Okay, good evening. Last time I talked about the underlying ideas of simplex algorithm, right? And today I'm going to continue to talk about simplex algorithm with a couple of example problems, okay? And last time I said before you implement the simplex algorithm, you need to convert the given LP to the standard LP, right? And then what is the standard LP? The standard LP is a linear programming problem in which all the constraints are equation, right? And all the variables are non-negative, which is greater than or equal to 0, right? So once you convert all the given LP to the standard LP format, then you can build up the initial simplex tableau based on that, right? And we've also learned that by introducing slack variable or the surplus variable, you can convert the inequality constraint to the equation, right? Okay. And this is the summary of ordinary simplex algorithm. Like it says, the first step is the optimality test, right? If every coefficient in the objective function rho is greater than or equals 0, of course, for the minimization problem, right? Then the current basic solution is optimal. Current basic solution is optimal. Otherwise, we need to determine the entering variable and then determine the leaving variable by applying the minimum ratio test, they call it. And then solve the new basic solution by using elementary row operations, okay, until you find the optimal solution. Excuse me. Okay, then let's consider a simple LP problem like this. I've mentioned before the simplex algorithm can be used to solve any LP. The given LP must be converted into the standard form, right? So to convert an LP into the standard form, like I said, for each constraint, we should have for each less than equals constraint, we should introduce slab variable, right? Which is the amount of resources unused in each constraint, right? And in this case, we introduce 3 slab variables, right? Let's say it's S1, S2, and S3 for each constraint. So our original LP has been converted to standard form like this. And I said the initial tableau for the simplex algorithm would be constructed based on this standard LP. And right after move Z into the left-hand side, the initial tableau for the simplex method can be constructed like this. So what do we have as basic variables? You remember any column corresponding to a basic variable in a simplex tableau should have only one non-zero, which is 1, right? So according to the initial tableau, negative Z, S1, S2, and S3 are the basic variable in this case. And the basic solutions are obtained by setting the non-basic variables to 0 and solve for the basic variable, okay? And the basic solutions represents the corner point. So I said initially S1, S2, and S3 are the basic variable, while the X1 and X2 are the non-basic variable. So they should have a value of 0, right, for non-basic variable. And this basic solution is one of the corners of the feasible region, which is polyhedron. The first step is to check the optimality, right? If there is no positive relative profit, then the current basic solution is optimal. Otherwise, we need to select entering variable, right? So if you look at the relative profit here, which means the coefficient of the objective function row, we see that the current basic solution is not optimal. Why? Because there are two positive values of relative profit, right? Which means increasing either x1 or x2 will increase the current objective function value, right? So in this case, we may arbitrarily select x1 to be increased, which means x1 enter the basis in the next iteration. And after you select the entering variable, the next step is to select the leaving variable by performing the minimum ratio test, right? And the minimum ratio test in this case would be (150 over 5, 100 over 2, 80 over 4, which is 30 and 50 and 20. So 20 is the minimum value. So minimum occurs at 20, right? Which means as we increase x1 from 0, the first block occurs at 20, right? Where the corresponding variable, which is s3, becomes 0, right? Which means s3 should leave the basis in the next iteration. Is that right? And the geometric representation for the minimum ratio test would be like this. Because the current basic solution is not optimal, we need to move to a better adjacent corner point from the origin, right? So for this example, increasing either x1 or x2 will increase the objective function value. So in this case, you may arbitrarily choose one of them to be increased, right? And some people might say we must choose x1 to be increased because the objective function is maximized 12 times x1 plus 8 times x2. Says moving up x1 axis will increase the objective function value much more than other case. But it doesn't mean that you will get the optimal solution faster. Okay? Let's think about this case. Let's just suppose we are dealing with maximization problem. And starting from the origin, you might say that we should choose x1 to be increased. Because moving up, let's say, highlighter. So, starting from the origin, we should choose x1 to be increased because moving up the x1 axis increases the objective function value this much. Is that right? Whereas moving up the x2 axis increases the objective function value only this much. Is that right? So you might say that moving up the x1 axis increases the objective function value at a faster rate than moving along the x2 axis. However, it doesn't mean that we will get the optimal solution faster. Suppose the optimal value has been found right here. Okay? In this case, starting from the origin, if you choose x2 to be increased, then you will reach the optimal point within 2 iterations. First iteration, you reach this point, and next iteration, you can reach the optimal solution. Right? And if you choose x1 to be increased, the objective function value will be improved a lot on that iteration, like this much. However, you will need another 4 more iterations to reach the optimal point, right? Which is less efficient. Does that make sense? So in this case, we may arbitrarily select one of these 2 variables to be increased. This also means that the variables to be increased becomes basic variable, right? Which means it enters the basis in the next iteration. You remember last time I said the value of non-basic variable is always 0, right? Whereas the value of basic variable is greater than or equal to 0, right? So let's arbitrarily choose x1. So the value of x1 will be increased, which means that we choose to move along the edge that leads up the x1 axis. And the minimum ratio test tells us that we must stop at the first new constraint boundary, right? So if you move further, you will leave the feasible region. So if you make a mistake in minimum ratio test, in the next iteration, you will be outside the feasible region, which means you will have infeasible solution in the next iteration, okay? So the minimum ratio test is very important in the simplex algorithm. Now you come up with this new tableau resulting from the pivot. And based on this new tableau, our new basic solution would be this blue point, right? That is, we can say that the pivoting has taken us from one corner to an adjacent corner point, okay? And if you look at the relative profit, that is the coefficient of the objective function row, we can see that the current basic solution is still not optimal. Because there is a positive value of relative profit, which means that the objective function may be increased further by increasing x2. That is, now x2 should enter the basis. And just let you know that only ratio of right-hand sides to positive substitution rates are used in the minimum ratio test. And this minimum ratio test tells us as we increase x2 from 0, the first block occurs at 30, right? Where the S2 variable becomes 0 value, which means S2 leave the basis, okay? Now we come up with this new table resulting from the pivot. And based on this new table, our new basic solution would be this blue point, right? So we may say that, again, pivoting has taken us from one corner to another adjacent corner point. And please look at the relative profit on this table, the coefficient of objective function row, right? So does the current basic solution is optimal or not? Because no variable has a positive relative profit at this moment, so we may conclude that the current basic solution is optimal, right? Which means our optimal solution is like this. Negative g equals negative 300, which means our objective function value, g is 300, right? And x1 is 5, x2 is 30, and s1 is 65. Okay? Of course, you should be able to get the same optimal solution from this final table, right? Here, negative g equals negative 300, right? And here, x1 equals 5, x2 equals 30, and s1 equals 65. Okay? That's the optimal solution. Okay, now we will see what happens if we make a mistake in performing the minimum ratio test. Okay? Suppose in the first table, we had mistakenly choose to pivot in row number 2 rather than in the correct row, which is row number 4. Okay? And then the result is a table with a negative basic variable. So we can say that if you make a mistake in minimum ratio test, the resulting table is infeasible, right? See, one of the basic variable has the negative value here, down here, which is negative 40, right? In that case, S3 equals negative 40. But we assume that all the variables, decision variables, are non-negative, right? So we have an infeasible solution in this case, which is undesirable, right? And again, this can be explained geometrically like this. So in that case, this pivoting will take us to an adjacent corner point. However, outside the feasible region. Okay? This is this point that is outside the feasible region. Right? And at this point, x1 equals 30 and x2 equals 0. The slack variable for the third constraint, which is S3, is negative, which means the third constraint is violated. Okay? Okay, then let's consider another example. Again, before this simplex algorithm can be implemented to solve an LP, the given LP must be converted into the standard LP, right? So to convert an LP into the standard form, for each less than equals constraint, we need to define a slack variable, right? So in this case, we introduce two slack variables, S1 and S2, for each constraint like this. So our original LP has been converted to the standard form like this. And I said the initial tableau for the simplex algorithm would be constructed based on this standard LP. Again, right after move G into the left-hand side, the initial tableau has been constructed like this. So based on this, what do we have as basic variable? Negative G and S1 and S2, right? And if you look at the relative profit, we see that the current basic solution is not optimal, right? Because there are two positive values of relative profit. which means increasing either x1 or x2 will increase the current objective function value. So in this case, we may arbitrarily select x1 to be increased. That is, x1 will enter the basis. So as we increase x1 from 0, the first block occurs as 3, where the S2 variable becomes 0, which means S2 leave the basis. And we come up with this new tableau resulting from the pivot. And if you look at the relative profit again, the current basic solution is not optimal yet, right? Because there is a positive value for relative profit, which means increasing x2 will increase the objective function value. So in this case, x2 will enter the basis. Okay? The first block occurs at 6 over 2.2. In that case, S1 variable becomes 0. That means S1 leave the basis. And we come up with this new tableau resulting from the pivot. And based on this tableau, there is no positive relative profit. So the current basic solution is optimal, right? And because there is a 0 value of relative profit, that is increasing S2 variable will not affect on the objective function value, which means it really doesn't matter whether S2 enter the basis or not, right? So if we decide to include S2 as a basis, then as we increase x2 from 0, the first block occurs at 2.18 over 0.182. Because only ratio of right-hand sides to positive substitution rates are used in the minimum ratio test, right? And in that case, S2 becomes 0. That means S2 will leave the basis. So we come up with this following table, and we realize that we have the same objective function value with different set of basic variables, right? So for the first case, we have the objective function value of 12 with x1 equals 2.18 and x2 equals 2.73, right? And for the second case, we still have the same objective function value, but the x2 variable has the value of 2 and s2 variable value of 12, right? And this shows the graphical representation of this case. In this case, every point on this edge, including the corner points, is optimal. Okay? Only the two corners are the basic, however. Okay? So the statement, every optimal solution of an LP is a basic solution, is a false statement, right? Because in this case, the midpoint between these two optimal corner point solution is optimal. But they are not basic, right? You mean the basic solution is the corner point solution, right? That is the extreme point, in other words. Any questions so far? Okay, let's consider then another example. Again, before the simplex algorithm can be implemented to solve an LP, the given LP must be converted into standard form, right? And in which all the constraints are equations and all the variables are non-negative. So in this case, we introduce two slack variables, S1 and S2. Well, actually, in that case, we need to introduce one surplus variable and one slack variable, right? For greater than equal constraint, we need to introduce surplus variable, but for less than equals constraint, we need to introduce slack variable. And both surplus and slack variable should be greater than or equal to 0, right? That's our assumption. So our original LP has been converted to the standard form like this, right? And the initial tableau for the simplex algorithm will be constructed based on this standard LP. And suppose that after one or more pivots, we obtain this tableau. Okay? And this tableau is not optimal because S1 variable has a positive relative profit. Is that right? So S1 variable is selected to enter the basis. However, the minimum ratio test provides no block on the increase of S1. And when a pivot column is selected, that is, a variable is selected for increase, but there is no positive substitution rate on which to pivot, then the solution is unbounded, right? And if this is a real-world problem, then this usually means that some error has been made in the formulation or in a previous pivot, because it is impossible to make unlimited profits, right? Okay, then next, what if an error is made in selection of the pivot column? With this table, either X1 or X2 or X3 should be selected to enter the basis, right? Because these two variables have positive relative profit, which means that the objective function value must be increased further. But by increasing either X2 or X3 variable, right? However, suppose we selected X1 column for the pivot by mistake. Then in the next iteration, the objective is worse, not better, right? The table on the bottom of this screen tells the z value equals 5, right? So it has been decreased from 13.3 to 5, which means the objective is worse. Okay? Okay, then now let's work through the simplex method step by step in tabular form to solve the following problem. Okay? And I'm going to use Excel spreadsheet. For doing this. Let's zoom in a little bit. And of course, the given LP problem should be converted to standard LP, right? By introducing three select variables, S1 and S2 and S3, right? So let's do this. So by introducing select variables, our problem can be converted to like this. Okay. Let's say 2x1 minus x2, x3. Subject to 3x1, x2, x3 plus s1 equals 6, right? x1 minus x2, 2x3 plus s2 equals 1. x1 plus x2 minus x3 plus s3 equals 2. And let's say this is equal to z, right? And move this z to the left-hand side, then we will have negative z plus this equals z equals 0, right? And based on this, let's construct the simplex tableau, initial tableau. Okay? So this is negative z column, x1, x2, x3, s1, s2, and s3 on right hand side. Okay. And let's put another column for basis. Okay. And let's zoom out a little bit. 50%. Is that too small? Is that okay? Is that small? A little bit? Okay. And let's put the coefficient of each variable. Okay, it should be 1, 0, 0, 0, 2, 3, 1, 1, negative 1, 1, negative 1, 1, 1, 1, 2, negative 1, 0, 1, 1, 1, and all 0. And right hand side value is 0, 6, 1, 2, right? Okay, now we have completed the initial tableau almost. Let me make a copy and paste it and delete all the values. And currently the basis is negative z, right? And the next basis would be S1, right? S1. And next basis is correspond to this, which is S2, right? And next basis is S3 variable, right? And because we are maximizing, right? So increasing either x1 or x3, both of which have positive relative profit, right? Is that correct? x1 and x3. So increasing either x1 or x3 will improve, which means increase the current objective function value. So we will arbitrarily select x1, okay? So entering variable becomes x1, okay? And, oops, sorry. As x1 variable increases, each of the basic variable, as x1 increases, each of the basic variable, which is s1, s2, and s3, decreases, right? Because of the positive substitution rate. And the minimum ratio test would be (6 over 3). Oops, what is that? Okay. Okay. Or 1 over 1. Or 2 over 1. Oops. So the minimum occurs at the value of 1, right? So the minimum ratio test indicates that the first to reach is lower bound of 0. As x1 increases is s2. Is that right? So x1 variable replaces s2 variable in the basis. Okay? And the pivot is to be done in the row in which the minimum ratio was computed. So actually this becomes the pivot cell. Okay? So basically we should make 1, 0, 0, and 0, right? In the next iteration. Because x1 variable enter the basis, okay? And we can do this by using elementary row operation, right? So we already got the value of 1 here, so which means we can just copy this value, right? And copy and paste it. Okay? And then how do you make 0 down here from 2 using this pivot value? I'm sorry? 1 over 2? What about this? Okay. Let's say objective function row is row number 0. Okay? Then the current row number 0 minus 2 times the pivot row, which is row number 2, becomes new row number 0. Okay? So in Excel, let's put this equation. So I'm saying row number 0 minus 2 times row number 2, right? Is that correct? And we've got 0 down here. What you need is just copy and paste it. Likewise, copy and paste it, right? Likewise, how could you make this 0 from 3 using this pivot value? The row number 1 minus 3 times pivot row, which is row number 2, becomes new row number 1, right? So in the Excel spreadsheet, let's just type in row number 1 minus 3 times row number 2, right? Becomes 0. Okay? So just copy this formula to all others in that row. Okay? And lastly, how would you make 0 from 1 using this pivot cell? Okay, right? So row number 3 minus row number 2 becomes new row number 3, right? So this is going to be row number 3 minus row number 2, right? Oops. And copy and paste it. Okay? So we have completed the next iteration, right? So based on this, what do we have as a basic variable? First one is negative g, right? And what do we have for this row? It's going to be S1, right? What about the next row? Which variable is basic? X1, right? What about the last one? S3, right? Which means in this current iteration, our objective function value, g, is 2, right? And the optimal solution, it's not the optimal solution. The basic solution is S1 equals 3, and X1 equals 1, and S3 equals 1. And all other variables are equal to 0, right? And as you can see here, our objective function value has been improved a little bit from 0 to 2, right? Okay, now let's copy this. Oops. Copy, paste it, and delete all the values. Okay. Then, if you look at the relative profit, which is the coefficient of the objective function row, is it the optimal? No, because there is a positive relative profit in the X2 column, right? Is that right? Which is therefore selected as the pivot column. Okay? So as X2 increases, if you look at this, S1 and S3 will decrease because of the positive substitution rate, which is 4 and 2, right? And the minimum ratio test indicates that S3, well, first of all, S2 becomes the entering variable. And the minimum ratio test indicates that S3 is the first to reach the value of 0. So the pivot is performed with the bottom row as the pivot row, okay? So this becomes the pivot cell. Okay? Again, we can perform the elementary row operation to make 1, 0, 0, 0 down here, right? Because X2 variable will enter the basis, which means the corresponding column has only one non-zero value, which is 1 down here, right? And all others are 0. Is that right? Isn't that easy? Right? So first, we need to change the value of 2 here to 1, right? So how would you do that? Just divide by 2, right? So let me write it down. First of all, row number 3 should be divided by 2. And then becomes the new row number 3, right? So it's going to be E11 divided by 2, right? Now we've got 1 down here, right? And just make copy and paste it, right? What about this? How do you make this down here 0 from -1? Oops. Using this pivot cell. How would you do that? The row number 2 plus 1/2 times pivot row, which is row number 3, becomes new row number 2. Okay? So let's put row number 2, which is this, right? Plus 0.5 times row number 3, right? Becomes 0 here. Just copy the formula and paste it. Okay, oops, sorry. Likewise, the row number 1 becomes 0. Row number 1 minus 2 times the pivot row, which is row number 3. Okay? Oh. So row number 1 minus 2 times row number 3, right? Becomes 0. Right? Likewise, lastly, the objective function row, this is row number 0 minus 1/2 times pivot row becomes new row number 0, right? So it's going to be row number 0 minus 0.5 times pivot row, this is row number 3, becomes 0, right? And copy and paste it. And let's complete the table. So currently we do have negative g as the basis. In the first row, the basic variable should be S1, right? S1. The second basic variable should be X1, right? The last one should be X2, right? Okay. Okay, then let me ask you, is the current Tableau optimal or not?
Yes.
It is, right? It is optimal. Because there is now no positive relative profits, right? In the objective function row. So therefore, the current basis is the optimal, okay? And the optimal solution is like x2 equals 0.5 and x1 equals 1.5. S1 is 1 and all other variables are equal to 0. And the corresponding objective function value, which is g, equals 2.5. Okay? Isn't it very easy, right? Okay, then this is another simple LP problem. And let's try to solve this problem with using Excel. Okay? So first of all, we need to introduce slack variable to convert this given LP to standard LP, right? So it becomes maximize 4x1 plus x2 equals g, right? Subject to 2x1 plus x2 plus s1 becomes 9, and x2 plus s2 becomes 5, x1 minus x2 plus s3 becomes 4, and both x1 is greater than equals 0, x2 is greater than equals 0, and all the slack variables S1 and S2 and S3s are greater than equals 0, right? And let's move g value to the left-hand side. So we will have negative g instead of having g on the right-hand side. Okay? And we can build up the initial Simplex Tableau based on this standard IP. Okay? Let's do this using XR. Okay. So again, let's zoom in 180%. Okay. Basis x1, x2, s1, s2, s3, and right hand side. Okay. And 1 0 0 0 4 2 0 1 1 1 1 negative 1 0 0 or I missed the G column, right? Zero, 1 1 1 0 0 0, and the right hand side is 954 0 9 5 4, right? Okay, we are almost done. So currently, the basic variables are negative z, right? And s1, s2, and s3, right? And let's make copy of this table and delete all the values. So in this case, either x1 or x2 might be selected to enter the basis, right? Because both have positive relative profit in the objective function row, right? And let's just arbitrarily select x1 to enter the basis, okay? For and let's put another column. It's a ratio, okay? So x1 enter the basis. So x1 variable will be the entering variable. The minimum ratio test says it's going to be 9 over 2, right? And another ratio is 4 over 1, right? And this will not be considered because in minimum ratio test, or the substitution rate should be positive, okay? So in that case, it's not available, okay? So minimum occurs at 4, right? Which means S3 variable will leave the basis as x1 variable enter the basis, okay? So this becomes the pivot cell, right? So we can just copy this value because it's already 0, right? And paste it through all other values in that row. And also we can just copy this value, right? Because it's already 0. And also we should make 0 down here and 0 down here, right? And in this case, this first row, which is R1, can be 0 using this. R1 minus 2 times R3, right? So let's put the corresponding formula, which is R1 minus 2 times R3 becomes 0, right? Lastly, the objective function row, R0 minus 4 times the pivot row becomes the new objective function row. Okay, so it's going to be this one minus 4 times the pivot row. Okay, becomes 0. And let's complete the table this way. Then currently we have negative g, oops, not here. And the first basic variable should be S1, right? What about the second basic variable? It's S2, right? And the last one should be X1, right? Okay, then, is this the optimal Tableau? No. Why? Yeah, because X2 variable, right? Because X2 variable has the positive relative profit in the objective function row, which means this X2 variable should get into the basic variable, right? In the next iteration. So X2 variable becomes the entering variable, right? Oops. And do the minimum ratio test. So it's going to be 1 over 3, right? And 5 over 1, right? That's it. And this is not available, because the substitution rate is negative, right? So the minimum occurs at 0.333, right? Which means S1 variable will leave the basis as X2 variable enter the basis. So this becomes the pivot cell, right? And let's copy this Tableau. And delete all the values. Okay. So in the next iteration, we should make 1 down here, and 0, 0, and 0 down here, right? Because the X2 variable becomes the basic variable. So first of all, the row number 1, this one, should be 1, right? So first, row number 1 should be divided by 3, right? So this becomes this divided by 3, right? And paste it. And how do you make 0 down here from 5 using this pivot value? Sorry?
Divide by.
Just divide by 3?
And multiply by 5.
5, right, great. Thank you. So the objective function row becomes 0 if you subtract 5 over 3, multiply the pivot row, right? And then the objective function row becomes 0. Is that right? So let me put that formula, which is row number 0 minus 5 over 3 times the pivot row becomes 0, right? And copy that formula and paste it through all other values in that row. Likewise, the row number 2 becomes 0 if you subtract 1/3 of pivot row from the row number 2. Okay? So let me put that formula. Row number 2 minus 1/3 of row number 1 becomes 0, right? Oh. And lastly, the row number 3 becomes 0 if you add 1/3 of row number 1 to the row number 3. Okay? So it's going to be this plus 1/3 of pivot row, right? Okay, becomes 0. And we are almost done, right? So currently we have basis, which includes negative z, and what is the first basic variable? x2. What about the second one? Is s2, right? What about the last one? Is x1, right? Okay. Is the optimal?
Yes.
No? Yes? Because each variable has a non-positive relative profit in the objective function row, right? So this is an optimal tableau. And the corresponding optimal solution to this given RP is that x2 equals 0.333, s2 equals 4.667, and x1 equals 4.333, and all other variable like s1 and s3, those two non-basic variables should be equal to 0, right? The corresponding objective function value, g, is going to be 17.7, right? Any questions? It's very simple and straightforward, right? Okay, this is all for today, and next time I'm continue to talk about the simplex algorithm. Okay? Okay, thank you. I'll see you next time.